In this section, we're going to be looking at the preparation of aldehydes and ketones. Now, everything that you have seen, or everything that you're going to see over the next couple of slides, are reactions that you have seen previously. And so, first one, we saw this one back in chapter 12 when we do the oxidation of a primary alcohol to an aldehyde, and we can use pyridinium chlorochromate. There are a couple other options, but PCC is sort of the go-to for this. If we want to take an ester, we saw this in the last chapter. If we want to take an ester and convert it into aldehyde, we can use dibal. If we want to take an acid chloride and convert it into an aldehyde, we can use the lithium tri-tert-butoxy aluminum hydride. And so these specific reagents go with those specific starting materials. Way back in chapter 11, when we talked about alkynes, we looked at the possibility of doing hydroboration followed by oxidation. That does give us an enal, but that enal tautomerizes to give us an aldehyde. So that is a possibility for synthesizing aldehydes. When it comes to ketones, we can synthesize ketones by doing the oxidation of secondary alcohols with any of our chromium-6 reagents. So chromium 6 oxide, and then these are usually mixed in with sulfuric acid. So we often refer to those as chromic acid. The sodium dichromate, potassium dichromate, and even the milder oxidizing agent pyridinium chlorochromate, or PCC. If you want to review that, go back and look in chapter 12. In the previous chapter, we looked at taking an acid chloride and using organocuprates to convert the acid chloride into a ketone. Very effective reaction there. In chapter 16, we talked about doing Friedel-Crafts acylation, and so this is a method of preparing aryl ketones, so where we have at least one aromatic ring directly attached to the carbonyl. Again, very effective. I've done this reaction dozens of times with different reagents. Very, very effective. And then we can also do hydration of an alkyne. A terminal alkyne will give you a methyl ketone. And if you do an internal alkyne, you'll get a ketone, not necessarily a methyl ketone, but you'll get a ketone. So just remember that when you're using a terminal alkyne, you need to use the mercury 2 sulfate as a catalyst. All right, one last method before we go on to work a few problems is looking at the oxidative cleavage of alkenes, which we can do with ozone. Again, go back and look in chapter 12 for a review of that. But if we have an alkene and we can oxidize it with ozone, we have to finish it up because this has an intermediate. Again, go back and look in chapter 12 if you want to see what that intermediate is. But we have to finish it up with either zinc and water or dimethyl sulfide. If the carbon that we're cleaving, if one of the carbons has 2 carbons attached, we'll get a ketone. And if there's at least 1 hydrogen attached, we will get an aldehyde. So let's go look at number 10 and 11 on our in-class assignment. All right, so we want to know what reagents are needed to convert each compound into an aldehyde, into this particular aldehyde. So that's the 4-carbon aldehyde, and unfortunately all of these have 4 carbons. When we look at this one, this is an ester. Converting an ester into an aldehyde, we need to use dibal. We'll go ahead and put the full reagents because that's usually how you need to know it. So we'll use the dibal hydrogen, so the diisobutyl aluminum hydride, and then follow that up with water. And when you follow that up with water, you will end up getting this aldehyde. And I will go ahead and draw that aldehyde so it's clear what aldehyde we're talking about. And then here, this is a primary alcohol. Converting a primary alcohol into an aldehyde is pretty easy using pyridinium chlorochromate. Okay. If we want to convert this terminal alkyne into an aldehyde, we need to do the anti-Markovnikov addition of H2O across the carbon-carbon triple bond. And the way that we do that is by doing hydroboration followed by oxidation. And so typically the hydroborating agent, it can be BH3. I'm going to put R2BH, and that gives us the full scope of possibilities as far as our hydroborating agent. And then in our second step, and this is important that you remember to do this, we use the hydrogen peroxide, H2O2, followed with the hydroxide. If you don't do that, you don't actually end up getting, you don't get the product. You have to do this, otherwise the boron's still going to be attached to the carbons. All right, on this next one, all we need to do is to cleave this carbon-carbon double bond with ozonolysis. And again, this is 2 steps, and you have a couple of choices for the second step. First step, using ozone, but then the second step, we would end up using either the dimethyl sulfide, or in this case, I'm going to use the zinc with water as our reducing agent to finish up the job. All right. Now we want to look at how can we make acetophenone. And just as a reminder, acetophenone, we've got the formula here, but go ahead and draw it. It's the methylphenylketone is that, but acetophenone is the common name that we typically see for that. And so here we want to convert benzene into acetophenone. So clearly we need to do a Friedel-Crafts acylation, and we can do that with acetyl chloride. So we don't need this sequential. I got sequential on the brain here. We just need the CH3COCl and then aluminum chloride as our Lewis acid to help that along. All right, for this one here, we have an acid chloride, and we want to convert that into a ketone. We need to use the specific reagent that converts acid chlorides into ketones. So we need that organometallic reagent, and the one that works specifically for this is going to be the organocuprate. And so we want methyl, so CH3CuLi. So it's the methyl organocuprate. And again, whenever we're using those organometallic reagents, we need to follow it up with water to finish up any of the reagent. All right. Finally, here we've got a terminal alkyne, and we can convert that into this methyl ketone, and specifically acetophenone. And our reagent here, we want to use water, H2SO4, and then whenever it's a terminal alkyne and we're doing this, we have to add the mercury to sulfate to make it work, and that will give us the acetophenone. That gives us our reagents needed to convert these compounds into that ketone. So this section has been mostly just a review of reactions that you've already known. I think it's important to point out that when you learn a reaction, you want to keep that reaction sort of in your toolkit so that you're able to access it anytime you want. And by your toolkit, I mean you need to memorize it, and so it can be tricky because there are a lot of reactions, but it is worth your time to organize those. I recommend making something like flashcards. And so whenever you get to like a new section where you've learned new stuff, go back and look at some of those old flashcards so you remember those reactions. It's very easy to forget them. All right, so now we want to look at different reactions that aldehydes and ketones will undergo. And we have quite a few possibilities, and there's two main categories of these reactions. The first category we're going to refer to as nucleophilic addition at the carbonyl carbon. This is the one that we've seen so far and that we've talked a lot about in chapter 17 and to some extent in this chapter, chapter 18. There is another category of reactions that happens with aldehydes and ketones, happens with other carbonyl compounds as well, but aldehydes and ketones are the ones that we're interested right now. Those are reactions at the alpha carbon. That is, reactions that occur at the carbon that is adjacent to the carbonyl. So for example, in this methyl ketone, so we have a hydrogen there. It turns out that hydrogen is a little bit more acidic than your typical carbon-hydrogen bond. So since it's a little bit more acidic, we can use a base to deprotonate that and create a negatively charged carbon, an anion. Well, this is called an enolate anion, and we're going to discuss this in great detail in chapter 21 and 22. So you will see that coming up soon. That can go on and react with an electrophile. I'm not going to get into the details now other than to say go ahead to chapters 21 and 22 and you will get a preview of those reactions. So let's talk about the nucleophilic addition. I have shown you the mechanism for nucleophilic addition before, but I'm going to go ahead and show it to you again. All right, we need to have a strong nucleophile, and if we can use neutral or negatively charged, mostly negatively charged, unless we're going to have an acid catalyst. I will show you the acid catalyst thing here in just a bit. But we do a nucleophilic attack on the carbonyl carbon. So nucleophile comes in, reacts with that carbonyl, kick the electrons out to the oxygen to make an alkoxide. We'll get this tetrahedral intermediate, which is the alkoxide. And then in a subsequent step, we need to protonate that oxygen to give an alcohol. And like I said, we have seen this reaction multiple times with different nucleophiles. Those nucleophiles sometimes are hydride in the case of our reducing agents. They can be our organometallic reagents, like the Grignard reagent or an organolithium reagent. And so we have many possibilities for doing nucleophilic addition on these carbons. Now, this is one that we haven't discussed up to this point, and it is acid-catalyzed nucleophilic addition. If we don't have a super strong nucleophile, like if we have a neutral nucleophile, or we have one that is not quite as strong of a nucleophile, then we can use a acid catalyst to help promote the nucleophilic addition. And so how that would work is first we can protonate the carbonyl, and whenever you have an acid catalyst, if you're not sure where to start the mechanism, start by protonating something. And in this case, we're going to protonate that carbonyl. When we do, we now have a positive charge on that oxygen, but we can draw an additional resonance structure that puts the positive charge on the carbon. When we average these together, we will get a partial positive on the carbon, but that partial positive will be a greater partial positive charge than we would get with just the carbonyl alone. So what this does is it activates that carbon. It makes that carbon more electrophilic. Then our weaker nucleophile, our neutral nucleophile, can then come in and react with that that electrophilic carbon. And when we do, we will get this intermediate, and we do need to deprotonate this intermediate with something. Typically, the conjugate base of your acid is one that we can choose, but it could be any number of things that happen to be in solution. And so we come in, deprotonate it, and we get our product. So nucleophilic attack. So, all right, protonation, nucleophilic attack, and then deprotonation to form our neutral product. All right, we're going to see that this is the basis for quite a few reactions that we do on carbonyls, and so we will look at that. Now, one thing that I think is worth pointing out is that something that we call a good nucleophile in an SN2 reaction doesn't necessarily make a good nucleophile in nucleophilic addition, or nucleophilic substitution for that matter. As an example, chloride, bromide, and iodide are all pretty good nucleophiles in the SN2 mechanism. So when we're doing a substitution at an sp3 hybridized carbon and we have a good leaving group, then these end up being very good nucleophiles. In the case of when we're adding these to a carbonyl, they end up not being very effective, and I can show you why. So here we've got our weak base, which is a good nucleophile for SN2, but not so much for nucleophilic addition. If it comes in and attacks that carbon and we kick the electrons out to the oxygen to make an alkoxide, well, we've gone from having a very weak base, which is the chloride, to having something that's a very strong base, which is the alkoxide. And so since this is our stronger base, then our equilibrium for this reaction would lie far to the left. So this is not going to be very favorable. So, again, we need to have different kinds of nucleophiles. We need to have much stronger nucleophiles than we do with the substitution reactions the SN2 reactions that we saw back there. Now, there are some nucleophiles that are good at both SN2 and this nucleophilic addition on a carbonyl. So let's look at some of the effective nucleophiles in nucleophilic addition. So we've already seen some when we did the organometallic reagents. Those were all very good. And then we also saw with the reducing agents, the hydride acts as a very good nucleophile. But we can also do another mechanism, which is kind of interesting, which is an addition-elimination process. So we have a good nucleophile, particularly something like an amine, and we will look at the example of a primary amine. The amine can come in, attack that nucleophile, and then we go through the protonation, deprotonation process to get this carbonyl amine. Well, that carbonyl amine is not particularly stable. We can eliminate OH and H across this carbon-nitrogen bond to give us an imine. And we're going to talk about the imine coming up in a later section of this chapter. And if you're interested in which section that is, that's going to be 18.10. So 18.10 will be the section where we talk about the formation of imines from primary amines. All right, so we're going to find that this is a fairly common process, and this is an example of something that we will often do if we form a product that would appear to be something that is stable, but it's actually unstable. We can enclose it in brackets, indicating that it's not going to stop there, and that we will do the elimination and form that imine. So now we're going to look at some examples of nucleophilic addition, and many of these are ones that you have seen previously, and some of them are going to be new. All right, so this is the list of This is the list of reactions that we're going to be discussing. So we've got reduction, all right, and we've seen reduction. We've talked about reduction of the carbonyl with a metal hydride. We saw that back in chapter 17. We're going to look at it again in the next section, but we're not going to go into it as much detail as we did then. We can also add organometallic reagents to the carbonyl. Again, we saw that back in chapter 17. We're going to briefly mention it here just for the sake of covering it here. We're also going to look at the formation of cyanohydrins, and that's coming up here in section 8 of chapter 18, so that will be here soon. And then this is a favorite reaction for a lot of organic chemistry students. It's called the Wittig reaction. And with this reaction, we actually will break the carbon-oxygen double bond and form a new carbon-carbon double bond. And this is a very cool reaction. I like this reaction. There's the reaction I just mentioned, which is where we take a primary amine and we react it with a carbonyl. We get an unstable intermediate with the carbonyl amine, and we end up getting an imine after we eliminate H2O. So reactions, and again, that's coming up in section 10 of this chapter. In the next section, we look at the reaction of a secondary amine with a carbonyl. When we do that, because there are not two hydrogens on that secondary amine, we end up getting something called an enamine. And there is a specific requirement that's not too difficult, but a specific requirement for this, and that we have to have a hydrogen on the alpha carbon. And then finally, we're going to wrap up this chapter talking about the formation of hemiacetals and acetals. And that ends up being an important process for protecting group chemistry and for looking at carbohydrate chemistry. So this is sort of an outline of things coming up in the rest of the chapter. So let's start with the addition of hydride across the carbon oxygen bond. So we add hydride to the carbon and we add a hydrogen to the oxygen. So we're essentially adding H2, but we do it in the form of hydride and then protonation in a subsequent step. We can do that with sodium borohydride or lithium aluminum hydride, as we have discussed. So, and you can form either a primary or secondary alcohol depending on what you started with. If you started with a ketone, you'll get a secondary alcohol. If you started with an aldehyde, you will get a primary alcohol. It is a two-step mechanism, and it's the same two-step mechanism for nucleophilic addition that we have been looking at. First, the attack of the nucleophile. In this case, we've got the hydride from lithium aluminum hydride comes in, reacts. We get our tetrahedral intermediate, that is an alkoxide. And with lithium aluminum hydride, we have to add water after this reaction is essentially complete. We add water, and that protonates the alkoxide to give us an alcohol. This is that case. If we put the water in with it, the water will react with the lithium aluminum hydride. So we don't want that. If we use sodium borohydride, the conditions are a little more mild. You pretty much just do the reaction in an alcohol, you add the sodium borohydride, and you get the reduction without having to add water in a subsequent step. So we talked about this back in chapter 17, section 4. So I'm not going to go into it in great detail other than to say you need to know this reaction. We can do nucleophilic addition with organometallic reagents, so where essentially we have a carbanion, and that can include organolithium reagents and Grignard reagents, and so if we have a ketone, we'll end up getting a tertiary alcohol. If we have a regular aldehyde, we'll get a secondary alcohol, And if we have formaldehyde, we will end up getting a primary alcohol. The mechanism for this is almost the same. We attack with the nucleophile. The nucleophile comes in. We form a tetrahedral intermediate, that is an alkoxide, and then we add water to protonate. All right, we talked about this in chapter 17, section 10, so worthwhile going back and looking at that if you want to refresh yourself on the details. All right, so here is a reaction that I don't believe we have discussed up to this point. This is where we can add HCN across a carbon-oxygen double bond, so add it across a carbonyl. And so we can do this with aldehydes and ketones. So we're going to add it across the pi bond. And so to do this, we need to have a mixture of two reagents. And these two reagents may seem counterintuitive to have both of them present. Here we use sodium cyanide, and which, by the way, is something you need to be extremely careful with if you're working with it. So this particular reagent is extremely poisonous, and it becomes even more poisonous when you start adding acid to your reaction. So you have to know what you're doing to do this reaction. So in other words, don't try this at home. Here is a specific example. So sodium cyanide plus HCl, and we can add that across. The reason I say this may seem counterintuitive to have both of these presents is that the cyanide is a weak base and HCl is a strong acid. So if you just mix these two together, it's going to convert all of that cyanide into HCN. The HCN is not a very effective nucleophile, so you can't just have HCN present. And also, you can't just have the cyanide present. If you have the cyanide present and you don't have some of the acid present, then what will happen is it will add, but you won't be able to protonate the alcohol. So it's kind of counterintuitive that you would have to have both. The trick is having the right balance, and when you add these chemicals, typically you'll put the cyanide in first, and then as it reacts, you will slowly add the HCl to protonate. This is another carbon-carbon bond forming reaction, and we know that these are very valuable reactions. Anytime we can bond two carbons together, that gives us a little bit more flexibility in synthesis. So we like these carbon-carbon bond forming reactions. Anytime you see a new carbon-carbon bond forming reaction, maybe make a special list for those carbon-carbon bond forming reactions. So let's look at the mechanism. And I mentioned that this was kind of interesting because we have something that's basic and we also have some acid present at the same time. And it's all about the stoichiometry, getting the right mix of these chemicals. So first, we do need the nucleophilic attack of cyanide on the carbonyl. So that nucleophilic attack, it comes in, attacks that carbonyl carbon. We get our typical tetrahedral intermediate, and that is an alkoxide, and then with some HCN that is present, which you would get by adding the HCl in there. The HCN that is present will protonate that O minus. It will protonate that O minus to give you this alcohol. And we call this, where we have a cyanide group attached to a carbon that has an OH, we call that a cyanohydrin. All right, so this reaction doesn't occur if you just add HCN. If you just add HCN, well, HCN is a gas. You can dissolve it in water, but if you just add HCN, you don't get the nucleophilic attack. If you don't have the acid, you don't get this particular step occurring. So you have to have both. And again, it's about getting the stoichiometry right and doing it in the right order. So there's a couple of cool things that we can do with cyanohydrins. One is that we can reverse the product. So we can reverse this reaction if we add a strong base. All right. So if we add a strong base, we can deprotonate that alkoxide. And in this case, cyanide can act as a leaving group. Now, it's unusual to have a carbon as a leaving group, but it can happen in certain situations. So cyanide can leave as a leaving group, and we can end up with a ketone or an aldehyde plus cyanide. And so this is a reaction that is possible. Another possibility is acid hydrolysis of the cyanohydrin. And so if you do the acid hydrolysis, you need to do this in aqueous solution. You can do acid hydrolysis. It's also possible to do base hydrolysis, but you also have to be careful not to get the base too concentrated. Otherwise, you'll get this top reaction occurring. But in this case, what happens is that we hydrolyze this cyano group to give us a carboxylic acid. So we hydrolyze that to give a carboxylic acid. All right, so let's look at number 13 on the in-class assignment. Pretty straightforward thing here. We have sodium cyanide and HCl, and that gives us the conditions for adding HCN across the carbonyl of this aldehyde. So our product is going to be a cyanohydrin. All right, and just so everybody's clear, there is still a hydrogen that is attached. The hydrogen that's in that aldehyde is still attached there. It's just implied. It's not shown in this particular example. All right, here we have a cyanohydrin that is already formed, and we want to see what happens when we do the acid hydrolysis. And so here we do this with aqueous acid and some heat. We can hydrolyze this into a carboxylic acid. So the OH will remain there, and then we will get the COOH as the product. Again, that's a carboxylic acid, and I'll go ahead and draw it the other way as well. All right, so that gives us that carboxylic acid. So there are cyanohydrins that occur in nature, and a couple of these. One is the I have to think about this one. The linamarin, I may be saying that incorrectly, and amygdalin. These are two naturally occurring cyanohydrin derivatives. These are kind of interesting because it is possible, if you consume either of these, it is possible that you can break this bond. This is essentially what we refer to as an acetal. We will talk about acetals coming up here in a bit, but we can break this bond so that we have the cyanohydrin, and then that cyanohydrin can hydrolyze to form cyanide ion. So if you consume this, you can produce cyanide in your body. In other words, that's really bad. That's really bad. So these are both naturally occurring products. So, this is one of those situations where somebody says, oh, here is a natural compound. Well, there's all kinds of natural compounds that are just dreadfully dangerous, and this is one of them. Now, amygdalin is something that you will find inside of a lot of different seeds, and the linamarin, again, I know I'm saying that wrong, but I forget how I was supposed to say that. It is found in the roots of certain plants, and the amygdalin is found in the seeds of certain fruits like apple seeds, plum seeds, and there's other ones. I don't remember all of them, but there's all these seeds where we don't eat the seed. Well, this is why we don't eat the seed, is because they end up being poisonous to us. So again, these things can get hydrolyzed. An enzyme in our body can break them apart to give us the cyanohydrin, and then that cyanohydrin is also converted via an enzyme to give us HCN. Your body is just trying to break it down and use it for fuel, and you have fed it a toxic chemical. All right, now there are certain people out there on the internet that will be pushing a compound called laetrile, and you can tell they're a hack if they start calling it vitamin B17. Well, here's the thing about vitamin B17: it is not a vitamin. Vitamins are things that they're essential chemicals that your body needs. This is definitely not something that you need. Laetrile has been used in certain use case scenarios for the treatment of cancer because it will definitely kill cancer cells. Well, the reason it will kill cancer cells is because it produces cyanide and it will kill those cells. If you take enough of this chemical, it will also kill you. So I am going to tell you, do not take this chemical unless specifically directed by a medical doctor. You'll see a theme in these. If somebody tells you to take a particular drug, medicine, chemical, make sure that a medical doctor approves that. Don't just trust random people on the internet. I think I've said that multiple times here. All right. So again, this does the same hydrolysis and will produce the HCN inside your body and will cause great damage if you consume it. All right, so now we're going to look at the Wittig reaction, which if you look at the pronunciation, I believe in German it's Wittig, but most English speakers will call it Wittig. Wittig, whatever. So the Wittig reaction, created by a German, George Wittig, all right, he came up with this reaction, very, very clever reaction. We use a specific carbon nucleophile, which is called the Wittig reagent, to react with carbonyls, and the product is a carbon-carbon double bond. So here are the reagents. We need either an aldehyde or a ketone. Either of those will work. And the Wittig reagent. The Wittig reagent is classified as something called an ylide. I will talk about that here in a slide or two. But that's our Wittig reagent. And there's also another way to draw this, which I will mention here in a moment. But it produces an alkene and triphenylphosphine oxide. In the process of doing this reaction, we form two new carbon-carbon bonds, a carbon-carbon sigma bond and a carbon-carbon pi bond. So we will form a full double bond that wasn't there before. All right, so here we've got an example aldehyde, and if we react it with this methylene Wittig reagent, we end up getting propene. So again, we've made a new carbon-carbon double bond. Here is another example. We've got this ethyl. And that ethyl, we will replace the oxygen here, and we will end up getting this. The driving force for this reaction is the formation of triphenylphosphine oxide. In particular is the phosphorus-oxygen bond. So that phosphorus-oxygen double bond, which we can draw a resonance structure for it that's a single bond, but that phosphorus-oxygen, regardless of what it is, that phosphorus-oxygen bond has a bond strength of, it seemed to be about 550 plus kilojoules per mole. And that's a very, very strong bond. That's on the same order as the silicon-fluorine bond that we saw earlier when we were talking about alcohol in chapter 17, when we were talking about silyl ethers and deprotecting those silyl ethers with tert-butyl ammonium fluoride. The fluoride makes a really strong bond with silicon. Well, we have a similarly very strong bond between phosphorus and oxygen. And so the formation of that phosphorus-oxygen bond is the driving force for this. It releases a lot of energy and makes this thermodynamically favorable. When it comes to the Wittig reagent, it is classified as an organophosphorus reagent. And here is what that Wittig reagent looks like. Here's the triphenyl phosphine reagent, so triphenyl phosphine, and then we have the carbon. And the way that it's drawn here, we've got a positive charge on the phosphorus and a negative charge on the carbon. All right, and this is classified as an ylide. Ylides are species that have two oppositely charged atoms bonded to each other while both still have an octet. And we've seen where we have two oppositely charged atoms where they don't have a full octet, but here you'll notice phosphorus has an octet and the carbon also has a full octet. Now, and then we'll see that these phosphorus ylides are called phosphoranes. So that is the category of these. These are called phosphoranes. So let's look at a resonance structure for a Wittig reagent. All right, so since the phosphorus is in period 3, we can draw a resonance structure where the phosphorus has more than an octet, has more than 8 electrons. So a second resonance structure would be, instead of drawing it where we have a negative charge on the carbon and a positive charge on the phosphorus, we can move these electrons over to form a pi bond between phosphorus and carbon. And that gives us, that eliminates the charge and gives us this particular structure. And I have seen both, I've seen both of these used in textbooks. And in this textbook, it draws both of them just to be clear that these are the same thing. These are not isomers of each other. They are resonance structures. And regardless of which structure we do use, we're going to find that, that the net charge on the Wittig reagent is 0. There is a significant partial negative charge on the carbon and a significant partial positive charge on the phosphorus. And so both of these resonance structures both have weight in their overall hybrid structure because there is some double bond character between the phosphorus and the carbon. So because of that significant partial negative charge on the carbon is a pretty effective nucleophile. So it is a pretty effective nucleophile. We're going to look at the mechanism of this in a few minutes, but for now, we're just going to see, let's draw the products of these reactions. I'm going to use in this problem on number 15, the book uses this type of structure where it has the double bond. All right, so here, you can kind of think of it like this. We have a carbonyl. We're going to break that bond. And we have a phosphorus carbon double bond, and we're going to break that bond. And this carbon's going to go with this carbon, and then this oxygen is going to go with the triphenyl phosphine. So our products are going to be, in this case, isobutylene and the triphenyl phosphine oxide. All right, here, again, we can think of this in terms of we're going to break that bond, we'll break that bond, and when we break those bonds, the carbons are going to get bonded to each other, the phosphorus will end up with the oxygen, and so we will have this as a product. One, two, three, four, five. 1, 2, 3, 4. So we'll get that plus, again, our triphenyl phosphine oxide. So Now we want to look at how do we synthesize the Wittig reagent. For most Wittig reagents, you would make these in the lab and use them right away. And it's a two-step procedure. And the first step is that you do an SN2 reaction between triphenylphosphine and an alkyl halide. Because this is an SN2 reaction, that gives you some limitations on what kind of carbon this can be. For example, if this is a tertiary alkyl halide, then this reaction is just not going to work. And if it's tertiary, well, then it's not going to work anyway because you wouldn't be able to do the next step, which is really important. So, so typically we use primary or methyl alkyl halides here, and in doing so, we can form a phosphonium salt. Now, this phosphonium salt is not the Wittig reagent, because you'll see that this species here has a positive charge balanced by the negative charge on the halide. We need to come in and deprotonate this in order to make it into the Wittig reagent. So we'll come in with a strong base. Typically, methyl lithium is a pretty good strong base to do this with. But we'll come in with a strong base, deprotonate it, and we will form our ylide. And again, we can draw that either where we put the electrons directly onto the carbon, as we indicated with this arrow and this picture, or we can draw that where we have a double bond between phosphorus and carbon. And those are both valid ways to draw it. So now let's look at an example Wittig reagent synthesis. So to synthesize, let's just start with this one. To synthesize triphenylphosphine with the methylene, first, we're going to need to do the SN2 reaction between triphenylphosphine and bromomethane or methyl bromide. This one should be a pretty easy SN2 because that methyl is going to be not sterically hindered. So this is a pretty easy reaction. We form the phosphonium bromide, so this methyl triphenylphosphonium bromide, which we need to treat with a very strong base, and in this case we've chosen butyllithium. So butyllithium is organolithium reagent. All right. So when we deprotonate with that butyllithium, we are going to get our Wittig reagent, and so here are the Wittig reagent structures. So let's look at number 16 on the in-class assignment. Go back over here. All right, so we want to come up with a way to synthesize these Wittig reagents. And so to do this, we just have to figure out what this is. So this is ethyl. So we'll start with ethyl bromide. And we'll treat that with the triphenylphosphine. And when we do, we will get this, which is going to be a bromide. And then we need to treat that with a strong base, a very strong base. And again, butyllithium is a great choice. And then that will give us this particular reagent. So the pH3P there. All right, so so we'll react our primary alkyl halide here with the triphenylphosphine. It will give us this phosphonium bromide, and then we'll treat that with butyllithium. That will deprotonate this, and we will end up with that Wittig. Okay, so let's look at this one. All right, so here we're going to have a secondary alkyl halide. That will work. If you attempt tertiary, you're not going to have any luck there. But triphenylphosphine. positive charge there, it will be the bromide. And again, we can treat that with butyllithium to get this product. All right, and then for our final one, here we're going to want the benzyl bromide. All right, we can do the SN2 reaction, so triphenylphosphine. And then that we treat with the butyllithium, and that will give us this particular product. All right, so now let's look at the Wittig reaction mechanism and how we use it in synthesis, and that will wrap up this particular video. So let's talk about the Wittig reaction mechanism. I am not, for my class, I am not going to make my students reproduce this mechanism on an exam. However, I do want you to understand the mechanism so that you understand how it is that we get our product. So first step, we have a negatively charged carbon that's on the Wittig. And again, you can use the resonance structure where it has the negative charge here. If you use the where you have the double bond, then just go directly from the double bond to this carbon with your arrow. And then we will take a pair of electrons here that will go to the phosphorus, and so we will make a new bond between carbon and carbon and a new bond between oxygen and phosphorus. As I mentioned earlier, oxygen and phosphorus really like making bonds with each other, so that's the driving force for this reaction. We eliminate the triphenylphosphine, or the triphenylphosphine oxide rather, and that new phosphorus oxygen double bond, that's our driving force. And here we end up getting this alkene. So that's our mechanism. And so again, I want you to understand that this is essentially a concerted mechanism to give you this. And then the next step, I mean, overall, it's a two-step synthesis, but the bonding of the carbon to carbon, oxygen to phosphorus, that all happens in one fell swoop. All right, so how do we use the Wittig reaction, and what are some limitations of it? Well, one limitation of the Wittig reaction is that we do get a mixture of stereoisomers. So, for example, if we take this aldehyde and this Wittig reagent, we will end up getting a mixture of diastereomers. So we'll get some of the E isomer and some of the Z isomer. And that's going to be largely determined based on energy differences of the transition states and which one we get more of. So it is possible we can get more of our more stable isomer, but we will have to do some separation. Here is an example of synthesis using the Wittig reagent, and you can use some fairly complex molecules. So here we've got this aldehyde. It is a conjugated aldehyde, but it is an aldehyde. And then this Wittig reagent, which we would have made from a halide. So this Wittig reagent, we can use it to react with that aldehyde, and we can get beta-carotene. Now, the predominant isomer here would be the E isomer, but you possibly could get some of the Z isomer where it was a cis bond here, and that you would probably need to separate. I don't know what the percentage is, but you would get probably some of the Z isomer. All right, so how to determine what the best starting material for the Wittig is? Well, it's going to largely depend on what bond it is you're trying to make. So, for example, if we're trying to synthesize this, well, clearly clearly this is the new bond that we have formed, is this carbon-carbon double bond. The question is, what would be the two components that make up the Wittig? Would the Wittig be this right half of the equation, and the carbonyl compound be the left half, or would it be the other way around? So here, if we have the Wittig reagent as the right half and the carbonyl compound as the left half, we end up with these as our starting materials. If we do it the other way around, we're going to have this aldehyde and this triphenylphosphine Wittig reagent. So when we compare these two reactions, like which one of these is going to be the easier one to make? Well, the easier Wittig reagent to make is going to be the one that is less substituted. Because we have an SN2 mechanism in forming the triphenylphosphonium ion, because that's an SN2, the less substituted is going to be usually preferred. So here we've, with pathway 1, we've got a primary alkyl halide that we do the SN2 on to form the phosphonium ion, which then gives us the Wittig. Possibility 2, we have to start with a secondary halide. As I mentioned before, it's definitely possible to make a secondary halide, but you're probably going to have better luck with the primary halide. All right, finally, we want to look at what are some advantages to using the Wittig reagent for making double bonds as opposed to doing an elimination reaction, for example, with sulfuric acid and an alcohol. And the main advantage is selectivity as to where the carbon-carbon double bond goes. We can also get rid of the problem of having rearrangements. That is a common problem with elimination reactions. So if we want to take, for example, cyclohexanone and convert it into this alkene, well, that's a particularly challenging alkene to make by an elimination method. And so let's look at the two possible methods. If we did this where we had a cyclohexanone and we treated it with a methyl Grignard to get this tertiary alcohol, and then attempted to do an elimination reaction with sulfuric acid, we would get some of our product. But our primary product, our major product, according to the Zaitsev's rule, is going to be this more substituted, the tri-substituted product here. So we would get more of that product than we would of what we intended. When we do the Wittig reaction with cyclohexanone, there's a couple of advantages here. One, we do this in one step, and two, this is our only product. So we're going to get a much better yield by converting this cyclohexanone directly into our product than we will by doing the Grignard and then doing an elimination and then having to separate out the unwanted major product that we got. Okay, so let's look at number 19, and this will be the last one of this particular video. All right, so show two methods to synthesize each alkene. One method, one-step method using the Wittig reaction, and a two-step method using the elimination method we were just looking at. All right, so we're attempting to make this carbon-carbon double bond from this. So if we take that starting material and we treat that with our Wittig reagent, which is our triphenylphosphine, CH2, then we will get this as our only product. Oh, not carbon there, or not oxygen. I need to get rid of that. It's just going to be carbon there. All right, so we should get that as our only product. And that's very a very succinct mechanism. I like that. If we were attempting to do the other method, and that's where we used a Grignard reagent or organolithium reagent, so CH3MgBr followed by a subsequent protonation with water, we would get an alcohol. All right. And then when we do the elimination with H2SO4, we're going to end up getting 3 different products. And I'll go ahead and draw what those 3 different products are. I clearly did not leave enough room for this problem. So our 3 different products are going to be 1, the one that we want, and 2, that we don't want. That would be one of them. And then the other would be that. All right, and to further complicate matters, this one has a diastereomer, and that diastereomer, yeah. So I mean, it has a diastereomer. So this would not be the major product. In fact, it would be the 3rd most abundant product. This would be our major product for this. So we can clearly see that the Wittig is going to be superior in this particular scenario. All right, I'm going to try to squeeze this in here. So let's do our Wittig reaction to form this. So triphenyl phosphine. All right, we put CH C6H5. So it's just going to be the phenyl or the benzyl Wittig reagent, and that would give us our product that we were interested in. All right, and all right, so that would give us the product that we want. Now let's look at the other possibilities. So here, if we treat this with, I'm going to make this a little bit longer. If we treat this with our Grignard reagent here, MgBr followed by water, we would get a tertiary alcohol. All right, so we would get that. So we would get that. And then when we did elimination, we would get 2 possible products. So if we did H2SO4, we would get elimination in the ring as one of our possibilities. Sorry, this is so small here. So that would be one of our possibilities, not the one we're looking for. And then we can also get the product that we are looking for, which is this. And as far as which one of these we would get more of, we probably would get more of this. It's an endocyclic carbon-carbon double bond. Exocyclic carbon-carbon double bonds are a little trickier, but we would get a mixture of them, and it would be better than the one over here, but we still would have a big separation to do. So we can clearly see that using the Wittig reagent is going to be a superior method in this scenario. All right, well, we're going to end this video. We're over an hour on this video, so in our next video, in case you're curious, our next video, we're going to start with the addition of primary amines, and we will look at the amines and enamines and stuff like that.